So today I'm going to introduce the course using handwriting. And this will be given to you later on. So when are we worrying about fatigue? So when a material is under dynamic loads, or so-called the fluctuating loads, Okay, so let's say we have, for example, a beam or a cylinder, and we are applying a load right here, and let's say it's against the wall on the left-hand side. If this is under a static load, then we can quickly calculate how much bending it's generating. Okay, so in order to calculate that, basically your shear diagram will look like this. Right? It's very simple, shear diagram. And then if you calculate the bending moment, for this case, hold on, is that the shear diagram? Oh, there will be forces along different directions. So how about we use some examples that we introduced in the class, so I don't need to spend too much time on calculating. So let's say I have bearing here, and bearing here, and let's say I have a load right here. So for static case, the shear will definitely be something like this, right? Because bearing, the reaction force located at both bearings will be facing up. So your shear diagram definitely looks like this. And for the bending moment, over here you take an integral. Here you have positive value. So this is definitely a line and having positive slope, like this, going up. Okay? And over here in this region, you have negative shear. So when you do an integral, you have negative slope. That's why your bending moment looks like this. And let's say you get this value. This is the largest bending moment you have. In this case, it will tell you the largest stress you will have basically is 32 n pi d cubed. This is how you can calculate the largest stress inside this cylinder. Okay, but this is for static problem. When you have this static problem, when you do that, basically you are deforming this in this way, right? And over here you have tension, and over here you have compression. So you can say right here this is where you have the largest normal stress. And the magnitude of this normal stress is this one. You can calculate this. Okay, so one interesting idea is that what will happen if you start to rotate this cylinder? Previously, no rotation. Now, if we start to rotate the cylinder, what will happen? So, let me make a copy of this. And move on to the next page. Next page. So what if this is no longer static, this is rotating? Okay? And let's put a label on top of the cylinder. So if I put a label right here, let me put a label right there. So because this is rotating, the label rotates as well. Okay? And when the label rotates to the bottom, it's under tension. When the label rotates to the top, it's under compression. So if you keep on rotating, this position at the label is under a varying loading condition. Sometimes tension, sometimes compression. So if you draw a plot, and if this is time, and if this is the, you can say, let's just say stress at the label. What happens is sometimes it's positive, sometimes it's negative. It's going to be like this. Okay, and the magnitude of those, basically, this will be positive 32 m over pi d cubed. And this will be negative 32 m pi d cubed. Okay? And over here we are under tension. Over here it's under compression. So if it's rotating, this material is experiencing changing loading conditions. It's up and down, up and down. Okay? This will cause a problem. When this is happening, the strength of the material will reduce as this cycle increases. So one key idea is that the strength of material decreases as the cycle time of fluctuating load increases. Okay? So we need to know how much the material will have a drop of its strength. We need to do experiments to understand the situation. So there were experiments This is like a critique experiments. So what they did was they apply reverse loading conditions with same amount, or just reverse loading conditions. Apply reverse loading conditions to a material. Okay? And so this is time. What does reversely mean? Reverse loading. That means it's like this, and here is sigma, and here is sigma as well. They apply same amount of stress on the material reversely, sometimes positive, sometimes negative. And they reversely apply this, and they want to see for how many cycles this material start to yield. For how many cycles it starts to yield. Okay? So, if they apply a small load, which means the stress is small, of course, you can have a larger amount of cycles right here, then you will yield. Because the force you apply is very small. But if you apply a force that is very large, maybe it cannot handle such a long cycle. Okay, so there are another way to do this experiment. So what they did was focus on, for example, 10 to the power of 6 cycles. Okay, they decide not to find the number of cycles. They focus on some amount, and then determine at what I should say, then determine the material will just yield at 10th cycle when it's under what amount of stress. Okay, so over here, they control the stress. They study how many cycles. But it's difficult to compare with different conditions. So they change the idea here. They focus on same amount of cycles. They just do 10 to the power of 6 cycles. And they start to change different amount of stress. Sometimes smaller, sometimes larger. So there must be a value. After a lot of experiments, they will find a value. And when they apply that value of stress, reversely applying to the material, like a fluctuating loading condition like this, right at the 10 to the power of 6 cycle, the material will about to yield. Then this number, they call this number endurance limit. Okay, usually they use sigma E. They call this endurance limit. Okay, so what does that mean? That means if a material is under sigma E, reversely for 10 to the power of 6 cycles, it will yield. Okay, so let me write it down. What does it mean? When a material is under a fluctuating load with sigma E, it will yield for 10 to the power of 6 cycles. Okay, I should say at, not for. Okay? So, this is an important reference for us to know how this material can handle fluctuating loads. Different materials has different material property. Sometimes a material can stay strong when it's under fluctuating loads. Sometimes not. Okay, so every material has a different number right here. Okay, so why do I care? Why do I care? There is such a number right here. Okay, so usually endurance limit can be as low as half of the ultimate tensile strength. It could be really low, and it's lower than, usually it's lower than yield strength. So in mechanical design, we don't want to see yielding. Of course, we don't want to see the optimal tensile strength, because that's already over the yielding point. It's the worst case. It's
所以一定要到10的6次方才会到 endurance limit。有可能之前就会。
By definition, they do experiment to make sure this number happens for 10 to the power of 6.
那它有一张衰退表啊，就是
Yes. So they have a table. They did a lot of experiments. They try smaller stress. The material doesn't yield when it's less than 10 to the power of 6. They try a larger number. It will yield before 10 to the 6. So they did a lot of experiments to find out what's this number. So we all agree when we study in fatigue, 10 to the power of 6 is the cycle time we want to focus on. Of course, you can focus on different number of cycles. But usually for textbook, they use 10 to the power of 6. That's the most usual cycle time metal will carry for his life. Yeah. So it's like a common number of cycles. Okay, thank you for the question. So usually this is lower than yield strength. Then it's not a good thing, because when a material is under some amount of cycle, the strength drops and it's becoming lower than yield strength. So what we had in the past, we have some design equations. So previously, we have design equations. For example, our stress needs to be less than yield strength, the most simple one. When the material itself is having a lower strength, that means it drops. My design cannot handle some loading after a certain cycle because this drops. The upper limit drops. Okay, so when you design for static load, you don't care about fatigue. You don't care about the endurance limit. But if you are designing for something that has to take care of fluctuating loads, then probably you need to take endurance limit into your consideration. So how do we handle this? One way to handle this is to study the amplitude of the fluctuating loads. So from this diagram, you can see a material could be under some kind of fluctuating loads. So in general, fluctuating loads lead to fluctuating stresses. Which means if this is time, then your stress could be fluctuating like this. This is a stress, okay? This is a general case. And how it fluctuates may not be studied easily. So we are going to study this in a statistical way. We're going to study the mean value and also the amplitude. So let's say this is the mean value. We can call this average, and we can call this sigma r, represent range. So I should do this. So AVG represent average. R means ranged. So in one of the textbooks that I read in the past, they use sigma AVG and sigma R. And in some other books, they use sigma M. M represent mean. And they use sigma A. A is amplitude. Same thing. Basically, this is your sigma AVG. This is your sigma R. It's the same idea, but different books tend to use different notations. Okay? So if we study this in a statistical way, basically, what's happening is you can say your material is under a dynamic loading like this. It's under a constant load plus or minus a ranged load. Okay, so it leads to average stress plus or minus range stress. Okay? The easiest idea to make sure we can handle a fluctuating load condition like this is to make sure this is always lower than your yield strength. So easiest idea for of your design for fluctuating load then could be okay. Can someone tell me why I don't put a minus here? Can someone tell me why? There's a plus or minus, but I don't put a minus here. Anyone knows? Can someone guess? Why? Yeah. Anyone can try to express your thoughts? How come I don't put a negative sign here? If I put a negative sign here, that means it's a different equation. This is one equation. The other equation has a negative. So basically two inequality equations, two design guidelines. But which one is more important? This one is more important. Why? Can someone tell me why this one is more important? Basically two scenarios. One is the upper limit, like the max load you carry. The other one is like the minimal load you carry. Like one would be this point, the other one is this point. So when I design, do I care about this one? Because it's under a smaller load. This is like the worst case. So usually for mechanical design, we worry about the worst case. What's the most serious condition? This is the most serious condition because it's under the maximum load. So when it's under this maximum load, we want to make sure this value should be smaller than yielding strength. Otherwise, your material will yield, right? So this is based on worst case condition. Okay? So, what's next? In textbook, it will try to make a drawing of this. But when we make a drawing, what should we do with the drawing? What would be the horizontal axis, y-axis, or what am I drawing? Okay, so they found out you can study the relationship between the average sigma and range sigma, and you can use it to draw a diagram. So let me show you what's happening. This is your average sigma. This is your range sigma. Basically, you treat this one as y, this is x. So it's like x plus y must be smaller than some number. And try to draw a line. And if this is a line, then you have a straight line right here. And let me show you. You have a straight line. Okay, and this is sigma y, sigma y. So this straight line represents equal sign condition for this equation. So if you have a load condition, it's on the left lower corner inside this triangle. It satisfies this equation. On the other side, it violates the condition. So in the future, if you are carrying another kind of fluctuating load, you can study how much average stress you are carrying, and also how much range stress you are carrying, and you plot out the coordinate, and just see if it's inside the line. If it's inside the line, you feel like you're okay. So that's the idea. If you have some design, it's carrying some average stress and carrying some range stress. For this particular design point, it's within the range. So this one is safe. So this point satisfies this equation. So consider as a safe design. For this model, this is a model. This is a mathematical model. And we call this model the yield line model. So they call this line yield line. Okay? So this is the simplest idea, to worry about range stress or fluctuating stress or amplitude stress, no matter what kind of name you want to call it. But remember what we said earlier. When we begin to have this fluctuating stress, as time goes by, more cycles you have, we know this value drops. Does that mean at some point this will drop to here, then this design becomes a failed design? That's true. So yield line model doesn't consider the drop of your strength due to fatigue. So yield model only considers the fluctuating stress, but it doesn't cover the idea of fatigue. Okay? So it covers the idea of fluctuating stress, but not yet considering the drop of strength due to fatigue. And of course, the low cycles. Okay? In this equation, you don't see it. You don't see this model is considering the fatigue and the number of cycles. So what can we do? We don't want this model to be too complicated. And the idea is there's another model, the second model. This is the first model. So there's a second model. It's called the Goodman. It's a person's name. The nicest person in mechanical design. Goodman. It's a joke. Anyway, I'm not sure if he's nice or not, but his name sounds like a nice person. Okay. Goodman said we should consider the drop of material strength. So I'm not going to go through how Goodman derives the model or modify the model. I'm going to show you how this new different model looks like in this diagram. I believe it's the most easiest way to understand it. So what Goodman did was, when you design, you should worry about the endurance limit along the y direction, y-axis. How come you worry about the endurance limit on this direction? Because this is the axis about range stress, and range stress is what's causing the cycles. So they are studying this fluctuating load in two independent ways. They treat the average one as a static load, and they treat the ranged one as the source of fluctuations. And previously we talked about, for fluctuating stress, you asked a question. For certain times of cycles, the strength drops to endurance limit. Okay? Actually, after this, it doesn't drop anymore. It's like the minimum. Okay? It drops really fast for the first couple 10 to the power of 6 cycles, and then it doesn't drop too much. So for greater amount, this is still okay. So right here, along the y-axis, which is representing how the stress is fluctuating, we cannot just considering the yield strength. We should consider the endurance limit. So it's like we assume it's going to carry cycles greater than 10 to the power of 6. So I should use this value as my design limit. Okay? But for Goodman, he feels like since this material is under this fluctuating load, so how many times this material is carrying the average load? Not much. Like if you take a look at this one. Only this time it's carrying the average load. And it drops again and then comes back. Only here. And it's above, now it's below. So sometimes only along this entire cycle, along this entire period of time, this material only carries stress of sigma AVG at only certain point. It's not carrying sigma AVG all the time. So Goodman would like to give more greater design limit for sigma AVG. It's his model. So what he did was he decided to allow the average sigma to be even greater than yield strength. So what is the value greater than yield strength? Basically the ultimate tensile stress. Sigma mu. Okay? So what he did was he drew a different line. So for this line, he believes a material has to carry dynamic loads within this red line, not the blue line. So this is Goodman's model. So in this case, what we had earlier is not satisfying Goodman's model, because what we had earlier was not under the consideration of fatigue. But Goodman take care of fatigue. Goodman utilized the endurance limit as the upper limit for range sigma. but he allowed more freedom along the average sigma. So he allowed this average sigma to be as large as your optimal strength. Okay? So later on, there is a modified Goodman. So what is modified Goodman? Modified Goodman is this red line, but over when it has a cross right here, it goes down to here. So this area, some people still believe is not safe. So the modified one is a straight red line right here, and then make a turn and go through the blue line. So let me, if you go this way, and then if you go this way, it's not, let me use a different kind of pen. Yep. So for the purple one, is the modified Goodman. So it really depends on which model you use. Okay? And some others even believe you should be more conservative. So there is a most conservative model. It's called Solderberg. Is the most conservative model. So how does the Solderberg look like? Let me show you. Okay, so for Solderberg, that it is using this one. The most conservative design. He directly connects the endurance limit and the yield strength. This model has the smallest design space. If you have a smaller design space, your design is more conservative. Okay, so those are the three models that we will use in the class. And of course, there are some other models, but they are nonlinear ones. I'm not going to cover the nonlinear models. If you are interested, you can check the textbook. Okay? Now, in the diagram, we have three straight lines, but mathematically we need equations. So let me show you the equations for all three models. So first one, second one, and third one. Yield line, Goodman, and Solderberg. Okay? And I design the way of how the equation look like so you can remember this more easily. Okay? Let me move this to somewhere else. Okay? And I would like to show you how we can memorize it. So previously this was AVG plus R smaller than yield. You can rewrite this equation in this form. You divide both sides of the equation by your yield strength. Then you have an equation like this. Okay? And we can use this format for the other two cases. I'm going to copy this guy. And move around. Okay? But over here, I need to get rid of this range, this one. So what's different? What's different is for Goodman, the average will be divided by sigma u. Range will be divided by sigma e. For Solderberg, range will be divided by sigma e. Can you see? Yes.
可是那 R 就是随机的嘛，那个 range。
Yes. Sigma average and sigma r are the values based on the problem. So they are like a design values. Those two are material properties. So if you have no loads, they are zero. If you have static load, this one is zero, but you have an average number. If you have like a sine wave of loads, average is zero. The average of sine wave is a zero, right? So in this case, you have zero right here, but the range stress is not zero. So for this case, if this is like a sine wave, the sigma average is zero, and this is your sigma r. It's not zero. So in this particular case, over here is zero. It's like a purely reversely ranging stress. Okay? And of course, those values are values based on your problem. If you apply a very large load right here, your design cannot handle it because it doesn't satisfy the equation. So this equation will tell you how much load you can carry.
可是如果这个 R 是在 Y 的之下，可是这样就超过 Goodman 的流线。
Do you mean negative value? You mean like here? Like here? Yes, if you have a design right here, for Goodman, it will tell you it's a failed design. You're right. So based on different models, they decide to use a different design limit. So this is the most simple design. It doesn't consider fatigue. So it's not a good design. It's not a good model to use. If you truly want to consider fatigue, you should use Goodman or Solderberg. Goodman comes early and gives you greater design freedom for the average stress. Solderberg is the safest. No matter for the average and the range, it guarantees you the material will not yield, both for range and static. But it's having a very small design space.
那如果我说把它变成一个方形，在蓝色。
Oh no, you cannot. Yes, if you have a square, which means you have a design right here.
那个点在一个焦点，红蓝线的焦点。
It's so for this one, it's only good for these two models. So it really depends on how conservative you are. If you are very conservative, this point is not safe. Okay? Thank you. Even when we have those design equations, when this equal sign happens, it will yield. So those lines are the limit state of your design. We call them limit state. So you don't want your design to reach the limit. It's too dangerous. So for those equations, we should apply safety factor. We also apply safety factor for fatigue models. Let's talk about how we apply safety models, safety factors. Actually, it's very simple. Okay, so how do we do it? Basically, we put our safety factor here. On the right-hand side. Same idea as the static model. We put our safety factor at the bottom of your right-hand side. That's how you apply safety factors. Okay? For all models, they are the same. So what does that mean if you apply safety factor? Diagram-wise, we can try to study it. So if this is yield strength, when you for the case of n equals to 2, that means you only allow this much smaller safe region. So if you apply 2 on the right hand side of your equation, you only allow half of your yield strength. That's why the design limit state reduced to half. This is only half if your safety factor is 2. So in this case, your design can only be placed inside this much smaller region. Okay? So how about the other models? Let's say this is our endurance limit. This is our ultimate tensile strength. Then half of it, this is half of your yield strength, and half of your ultimate tensile strength is here. In this case, this is your Goodman with a safety factor of 2. Okay, so it was right here. Now it reduced to by 2. Okay? And similarly, this line right here is Solderberg with safety factor of 2. Okay? So let's take a look at one of the design equation. For example, let's take a look at this one. So it's gonna be AVG over Y plus range of E smaller than safety factor. It's going to, the equation looks like this, right? And let's try to play with the equation and see what's happening. Remember, let's say it's a shaft under fluctuating bending moment and torque. So in this case, we may have average bending moment plus and minus range bending moment. For torque, average torque and range torque. So let's say we are having a shift that is under this particular case, a general case. The bending moment and the torque are both fluctuating. So if this is the case, then I have sigma average may equals to 32 moment average divided pi d cube. We may have sigma range 16 torque AVG. Range. Range pi d cube. And I may have what? I may have the tau average. Oh, so this part is wrong. My brain is not functioning. Sorry. This should be 32 m range pi d cube. This is 16 torque average pi d cube and tau range 16t range pi d cube, right? Because of this fluctuating low conditions, I can get those four. But let's take a look at our design equation. How do we handle stress? How do we handle shear stress? Can someone tell me? If someone can tell me how to handle this in this equation, he can leave the room right now. He doesn't need to stay here. He's a genius. Can someone tell me how do we handle? A shaft could be carrying bending moment and also twisting moment. And twisting will generate shear stress. But in our study, we never talk about shear stress. Do we not care about these? We do. Even, let's say we have a shaft, if we just keep on twisting it, it will break. It's pure twisting. So when you calculate the average and the range, they are under those two equations. You have average torque and your range torque. When you calculate, you do have a changing magnitude of your shear. You can calculate the average of your shear and the range of your shear, but the equation doesn't talk about it.
因为是1/2倍。
No. It's not an easy answer. That's why I said if someone knows, he can go. He doesn't need to come anymore. It's not easy. Okay, let me tell you one way to handle all of these inside our design model. The key is when we study fatigue, when we have average stress and range stress, we can use von Mises stress for this equation. So we can use von Mises stress. Can someone tell me why do we use von Mises stress here? Anyone? What will happen if we use von Mises stress? Can someone remember what is von Mises stress? It's an equivalent stress of what? Of all the load conditions. When we talk about the distortion energy model, so let's recall distortion energy model. We usually have a Moore circle, right? We first have a Moore circle, then we study the principal stress, and then we said the von Mises stress should be S1 squared plus S2 squared minus S1 S2. And we wish this should be smaller than yield strength over your safety factor. This is the maximum distortion energy model. And when we introduced von Mises stress, we said this is an equivalent stress that covers all loading conditions for the material. There's no direction in von Mises stress. It covers all the loading conditions for normal and shear. This is normal, this is shear, right? It covers everything. It's an equivalent behavior combining normal and shear stress conditions in the material. So if you use this, it's only one value, no direction. And it's an overall behavior for both normal and shear stresses. It's an equivalent stress that covers all stresses in normal and shear directions. So if we use this right here, if we use this here, this value right here, nobody is looking at me. Nobody cares. You guys, hey, everyone, nobody cares. Whoever is watching your cell phone, look at me. It's important. I'm going to talk about this only once. When you use von Mises stress right here, it includes normal loading conditions and shear loading conditions. It combines them into one value. Okay? We don't want to only know how to solve it. We want to understand what happened. This is why you are here. Okay? So use von Mises stress here will help you to combine shear stress into the equation. Let me show you how. So we now want to use Solderberg model. So this is a model, the most conservative model. Conservative model for dynamic loading. Okay? And we want to add safety factor inside. So in this case, my model looks like this, but I'm using von Mises stress. And here should be yielding. I'm using von Mises stress here. This should be, okay? So in this case, I'm using von Mises stress. So where von Mises stress, the average one equals to, there's an equation for von Mises stress. It should be 1/2 of sigma squared plus 3 tau q. So y, we need to know y from here, from this guy. So we need to know y, right? Let me show you why. So this is von Mises stress equals to this only when the low condition is for the shift. Only the low is being applied for a shift. So this is the equation of von Mises stress for general plane stress problem in a shift. Okay? And I'm going to show you why. So for plane stress problem in a shift, it looks like this. It looks like this. The low condition always looks like this. And the Moore circle is going to be like this. Okay? This is Moore circle. And basically, it's not a good drawing, but just quickly show you why that was the equation. Over here, this is your stress, and over here, this is your tau, sigma and tau. So the radius would be 1/2 of your sigma square plus your tau square. This is your radius. Yes, and your S1 equals to 1/2 of your sigma plus your radius. S2 equals to 1/2 of your sigma minus the radius. And if you plug in to the equation of von Mises, at the end you will have S1 squared, S2 squared minus S1, S2. Now I'm going to derive it. So it's gonna be sigma squared plus R squared. R squared is going to be like this. R squared is like this. Yes, and plus 1/2 of sigma times R. Yes, and also S2 squared is going to be like this. I'm deriving directly, and here is going to be negative sigma and R. And it's a huge root. Square root is a huge one. Minus, I cannot carry it in one line, so 2 lines. So minus 4 squared plus R squared. Okay. This is how it's look like. If I'm right. Oh, then and R squared. I need to write down R squared. R squared is this guy. Copy and paste. R squared is this guy. Okay, and then you can get rid of this and this. Get rid of this. Okay? Now let's see how it looks like. I should have oh, my equation was wrong. Sorry. My equation was wrong. It should be like this plus yeah. Should be like this. Okay, I remember I did it wrong. right here. So it's good that I derive it. Okay? So this is how, at the end, for that general shaft problem, this is a general one. If you plot out a more circle, you calculate the radius, you calculate S1, S2, and you truly derive the von Mises stress. At the end, it's a square root of sigma squared plus 3 times tau squared. Okay, so in this particular case, because we have average sigma and tau, average sigma and average tau, we can plug it into this equation at the end. This is your average von Mises stress. And this is how you can put your tau into the equation. So similarly, your von Mises range equals to sigma range squared plus 3 tau range squared. Okay, so let's put them together. So overall, you should have a crazy equation like this. Is this crazy enough? Not yet. Because it can be even more crazier if you do this. If you plug in the stress equation into it. So this is the final version of what's including. Watching these, we know. Watch at the bottom, we realize it's a Solderberg model because for the average one, the limit is yield strength. For the range one, the limit is your endurance limit. This equation considers safety factor. And also for the average stress, for the range stress, we're using von Mises stress. It's too long. How can someone memorize it? But if you follow my guidance and derive one by one, this is the combination of many different concepts. We put them all together. So I suggest you not to memorize this. You don't need to, but you need to know how we get this. Because that will help you to understand why we do this here, why we do this there. Okay? Next time, if possible, if I make a video of this, we need to focus on, we need to introduce another new concept. It's called stress concentration. It's going to be even more messier. They will be applied right here, right, oh no, sorry. Inside the bracket. Here, 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 and here. They are multiplier that indicate how stress increases due to the fact of stress concentration. Okay? So I will tell you a new idea called stress concentration. That's a factor that will make your stress, that will enlarge your stress. And if the stress is becoming larger in the design equations, those values become greater. But how do we estimate this? We will introduce it next time. Okay. You know, this part is the most difficult part in the lecture. So I suggest you guys pay attention. This is the most complicated part, and after we introduce this, the equation becomes so long, okay? And it combines so many concepts. All the concepts that we introduced in the previous lectures were combined together into one equation. Okay, so I will talk about stress concentration next time. Today, I will give you one homework. Okay, so how about this homework? Solve the exam 1 with the following additional conditions. Okay, so in order to describe this more precisely, I need to show you the problem. Did we have problems on internet? No? I didn't do it?
I'm not
Let me. Oh, I need to join internet first. Did I put anything in right here? This was the old one. I remember I put a MATLAB code, right?
Yes.
I only put the MATLAB code
Yes.
and the figures.
Yes.
Ah, I didn't. Okay. Then I can only recall how it looked like because I don't have it right now. It was. I remember we have a shaft. And we have, okay. We have belt right here, and I remember we have, I think, belt loads right here. And we have bearing. Right? This was the example. So previously, this is not changing. So I will tell you, okay, let me tell you what the problem is about, and let me tell you how to solve it. Later on, I will give you the complete description. So if I remember right, I don't remember which one is which. Basically, I have the distributed loads for the belt. So in this particular scenario, we are going to make the W's fluctuate. Okay. So it will be some number plus and minus some range. I will tell you what the numbers are. Okay. So for each distributed load, it's having an average value and also a range value. Okay. In that case, when you solve in that case, your reaction forces, remember we have reaction forces. Will also have average maybe a different index, and also range. We have 4 reaction forces. Because they fluctuate, then your reaction forces fluctuates as well. But it's very difficult to solve this problem. Why? Because this doesn't tell you how they fluctuate. It's a random noise. Sometimes this goes larger, sometimes this goes lower. They may not follow same time sequence. It's okay. We just focus on the worst case. So in order to study the worst case, we need to determine, okay, when this is having the largest, this is having the largest, each of them having the largest, we may have the worst. So there could be several combinations. So it's a kind of estimation. So everyone may study this in a different way. It's okay. There is no general solution because you may need to analyze it with your own assumption. So please write down your assumption, how you solve it. Okay, and I will also try to solve it in my own assumption. Later on we can discuss it. Which one makes more sense? Okay? So the scenario is easy. Basically, the belt fluctuates. The belt loads fluctuates. And let's see what's happening. Let's not focus on rotating. If it rotates, it's more complicated. So let's say it's not rotating. Yeah, let's not rotate this. So no rotation for the shift. Okay? And let's try to use Solderberg Model. And what do we solve for? We will solve for our safety level. So I will give you all the load conditions and also material properties. What you need to do is to plug in the equation. So you will know everything on the left-hand side. No consideration of stress concentration yet. And you need to think about how to plug in on the left-hand side, but we don't tell you the safety factor yet, right here. So this is something you want to calculate for. You have everything on the left. At the end, you will know how safe the design is based on our consideration. So when you try to solve this, you may feel a little difficult because I didn't solve any problem in front of you. During the weekend, I will find some time to make some videos about this part of the lectures. And also, I will try to solve some problems in videos. And I will announce it in the Facebook. So later on, please stay tuned to the videos. Next week we have an exam, right?
Yes.
Monday?
Monday.
Okay, so next Monday we have our second exam. It's nothing about fatigue. So don't worry about this homework yet. I will give you 2 weeks for this homework, okay? So this homework in 2 weeks. Because next week you will have exam 2. Next week, next Monday, is your exam 2. So what's going to be included inside exam 2? Basically, the maximum shear stress model, maximum strain energy model, maximum distortion energy model. Von Mises stress. And of course, in order to solve for this, you of course need to know how to study principal stresses using Moore's circle. And I probably will not ask you to solve for beam problem, because that takes too much time. So I would say second exam is the easiest one among the 3 exams. Because the first exam takes a lot of time to calculate, and it's easy to make a mistake somewhere. But for the second exam, I think I will give you a load diagram. I may give you something like this. I will say, okay, there's a material, it's under this load. You directly draw the Moore's diagram, circle. You can calculate the principal stresses. I may ask you to tell me the safety factor based on different kinds of models. Basically plug in the equations. And I may ask you, okay, what's the von Mises stress? If you know how to do this, exam 2 should be pretty easy. Okay? So we will get rid of what you need to do for exam 1, because that's too long. Solving for a beam is taking too much time. Okay? I may give you 2 problems. I don't know. Depends on my arrangement later on. Okay? So any questions for today? Okay.